Let me just check the volume on this microphone. We can probably put it up a little bit, not too much. Erica, are you here yet? You asked me yesterday about METI, and I looked it up. All right, for the rest of you, Erica asked the question about METI. SETI is the search for extraterrestrial intelligence. METI is intending to communicate, and they're sending out very high-powered signals to tell somebody we're here. And it's very controversial, and the people at SETI have denounced it, saying the decision to communicate with extraterrestrials intentionally should be made by humans as a whole, not by you just because you've got a big telescope and you can do it.
How about that for a public participation exercise? 7 billion subjects.
7 billion people vote on whether we should communicate with ET. Okay. So anyhow, I did look it up for you. Right. Oh, it's a program called METI, and that is Messaging Extraterrestrial Intelligence. And they've got pretty high-powered radio telescope and transmitter, and they're sending out beams at neighboring stars in the hopes of communicating and getting an answer. And some people think that's dangerous. I suspect not. The aliens.
But where is this in Ireland? Is it in Ireland that they're doing that? Where are they seeing?
Oh, I think California. I mean, where do things like this happen?
Is that the Yuri Milner that Starshot group that is trying to get together? Is that part of METI?
Oh, I think, is Yuri Milner's group part of METI? I think not. And one of the people who signed the declaration that they disagreed with METI was Elon Musk. So they got some pretty big names just saying, wait, no, maybe Elon Musk wants it for himself. But let's trust that, in fact, they're being honest and they would like this to be a universal international decision instead of just somebody who's got the money sending out signals. And yeah, I was just answering a question. Let's go to the talk, and then we'll come back to questions. So welcome back, everybody. You may think I have good timing, but I have help here. I've just reset it. Today, we're going back to the Kepler space mission, and also to a little bit to TESS. And yesterday, we were looking at the discovery of planets around other stars. That's what the Kepler mission was built for, to do very high precision measurements of stellar brightnesses to find the dips that would give them the planets. But what came along with that was the ability to measure the light variations in stars to exquisite precision. And most of the publications that have come out of the Kepler mission have been on the stars, not on the planets, because they've just changed the way we do our stellar astrophysics. One of the greatest things that the Kepler mission's been able to do is it's made the field of astroseismology, which I will tell you about today, able to determine the masses and the radii of the stars, which we need to know what the masses and radii of the planets are. So we astronomers are getting all this data to study the stars, and then we feed that information to the planet hunters so they know their planets. And it's completely mutually cooperative. We're a very collegial community. We work together in great cooperation. I got a message from a journalist in the US a few years ago, writing for this magazine, Science News, and he wanted to write about all the strange and weird things the Kepler mission was finding for stars. And that's where the title of today's talk came from, was from this article that he wrote. I've already been asked the question about Tabby's star. Tabitha Boyajian in the United States and her team found a star in the Kepler data, which they proposed had a Dyson sphere around it from an intelligent civilization that had gone extinct and the Dyson sphere was breaking up. What does all that mean? Well, first of all, the proposal is Freeman Dyson suggested that very advanced civilizations would build solar cells. You know, we're putting them up here. Have you got some on your roof? Well, the suggestion here is to put solar cells up, but in a sphere which completely surrounds the star so you catch all the energy from the star and then put it to use for yourself. This is really greedy. And in this idea, it's been done, and then the thing's falling apart. There's nobody left to take care of it for whatever reason. And there's the artist's impression. And when they put that idea out, it hit the news and got lots of excitement. Here's what they actually saw. This is a light curve from the Kepler data. This is actually a light curve I plotted because I've got the same data in my computer. I just wasn't the first one to look at it. Tabby was, and she ran with it. It's doing very well. So we're all looking at this stuff, and we're picking up different things. We've got more data than people. We're not actually fighting over who gets to discover things. We're trying to get more people to come work with us because there's so much to discover. So this is time here. And you can see we've got 90 days along the bottom. This is time in days, and I won't tell you in detail about this Julian date, but it's a counting system we use so that all times are positive from about 3,600 BC. You'll learn tomorrow when I go to the calendar why we need something like that. The calendar's a mess. This is how bright the star is, and so you can see that over the 90 days, things are passing in front of the star. It's dipping in brightness. And am I echoing too much? Are you okay there, Nicholas? All right. Things are passing in front of the star, and here's some huge things passed in front of the star and blocked out 20% of the light. How big does something have to be to block out 20% of the light of a star? And the answer is as big as a small star. But when one star passes in front of the other, and I'll show you that in a moment, you get a nice smooth dip. This isn't smooth. This is some irregularly shaped thing, and then here's some more things, and then there's another thing, and it's not regular at all. Hence, they proposed this weird thing with little gaps in it. Well, nobody believed that, but it got a lot of attention. It got a lot of people working on the star. And a year ago, after several years more work from the ground, Tabby and her team had another press release where they think they've got a much better model for this, much more physical. So there's a report from space by Deborah Bird, who runs the STAR program for the last 30 years out of Texas. Here's their idea now, that there's a disk around this star of material with giant comets. Now, we don't know any other star like that, and so there's no precedent for it. Comets are usually very tiny, but it's an idea that at least is based in physics rather than alien civilizations dying out with megastructures. Keep your ears open for this. Maybe this is right. It's a best model right now, but maybe something else is happening. This is a star I found in the Kepler data set very early on. A whole bunch of us started working on it, and it turns out to be absolutely remarkable. Unfortunately, our group just sat on everything we had learned for several years until another group published it all, but they got the same answers we had, and I don't really mind that. It's out there now. Stars often are binary stars. If you look at the Gemini twins, Castor and Pollux, Castor is two stars orbiting about each other with two other stars orbiting about each other, and those two go around each other, and over here's a little pair of red dwarfs called YY Gem, and those two go around that four. There's 6 of them. And not uncommon. This star, with this nice romantic name, Kepler Input Catalog 4150611. On the top, we've got 8, 16, we've got a month's worth of data here. This is how bright the star is in parts per 100, if you like, 3%. You can see that it dips on an 8.8 day time scale, and here it's blowing up. This is 1, 2, 3, 4 days. You get 2 dips, one slightly deeper than the other, lots of little wiggles. So one of the stars is vibrating, and the star's in an eccentric orbit. Remember Kepler's first law? The objects move on ellipses. This is an eccentric ellipse. The 2 stars are like this. They're perfectly aligned. One passes in front of the other, whips around and passes behind it, and then it goes out for a while. Comes back, eclipse, 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 eclipse. And so on an 8.8 day time scale, the 2 stars pass in front of each other and then coast in front of each other. It's an eclipsing binary. And when you've got an eclipsing binary like that, you can figure out the masses. Kepler's third law, we're interested in finding masses. That's good. But this, when I first found it, went into a box on that computer I call what is it stars. I've got lots of what is it stars. I don't know what they are yet. We do know what this one is. But we first looked at it. Every 92 days, here are the 2 dips up there, different scale over here. We've scaled it up a bit. Every 92 days, 3 things pass across the face of the biggest star. 3. 3's a problem. How can you get 3 things You know, two things is okay. You got two stars orbiting each other, but three stars orbiting each other, not so stable if they're close. We figured it out after a while. Here's what's happening. There's a big star, the kind that I work on, and it's vibrating. That's what's producing the wiggles. There's a pair of stars over here that are like the sun, both of them. They're going around each other in 1.5 days. But those two go around this one in 92 days, and they pass in front of it. But there are only two of them. How do we get the three dips? They're so far out, it takes over 24 hours to pass in front of the big star. They go around each other in 1.5 days. One comes across, here comes the second one, but the first one gets thrown back in its orbit, and it gives us another dip. So we've got two stars orbiting this one big one, but the two dips you see up there come from another pair over here that are doing this whoop, 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 whoop. So there are 5 stars up, but there's another pair in there too. There's 7 of them. And they're all tugging each other about, and with all those tugs and with Kepler's laws, we have determined the masses of these stars to the highest precision of any determination ever other than the sun, to a precision of about 1%. And so this is a record holder for us in our goal to find precision. Here's another what is it star when we first found it. It was the first of the heartbeat stars. It's called Kepler Object of Interest number 54. So Bill Baruch's team was grabbing the goodies, planets to start with, and calling them Kepler Objects of Interest, but if they saw something really weird, they'd grab that too. And working on planets, they couldn't figure it out, so they passed it on to the stellar astronomers, us. And we look at it. This is 80 days along here, and this is how bright the star is. That's about 0.8% difference in brightness here. And you can see the stars wobbling, and every 42 days it goes blip, 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 blip. We thought that looked like an electrocardiogram. We didn't know what it was, but we called it a heartbeat star. And we figured it out. We folded the light curve and piled all these blips on top of each other, and the wobbles all lined up too. And what that turned out to be, 2 stars in a very eccentric orbit. Remember Kepler's laws? Stars are moving on ellipses, in this case a highly eccentric ellipse. And these 2 stars, they've got an orbit a bit like Halley's Comet, if you've ever seen it. It goes way out and then comes in and whips around the sun. These 2 stars go whoomp, whoomp. And as they go whoomp, they almost collide, and the tides stretch them out of shape, and the stretch produces that big blip. We've had the theory of this for many decades. It's the first time we ever saw it. Now, we've got a colleague on our team by the name of Jim Fuller. Jim did his PhD 3 years ago now in New York State, Rochester University, and he's absolutely brilliant. He landed the best postdoc in our field on the planet. He was employed jointly by Caltech University and the Kavli Institute of Theoretical Physics. And in terms of theory, this guy can do almost anything. So he not only calculated what was happening, but he made us a nice little animation. So there's our 2 little wobbling stars. Down on the bottom is the light curve from the wobbles, and then as they pass and almost hit each other and stretch, that's what produces the heartbeat. Well, as you watch that, let me tell you a little story. 11 years ago, I had an undergraduate student sit in my introductory first-year astronomy class. She sat at the back of the class, and she was the top student in the class. She finished her undergraduate degree and did a master's degree with one of my colleagues in extragalactic astronomy. And then she came to a talk I gave and decided she wanted to do her PhD with me, and the timing was just right. I gave her the heartbeat stars, and she ended up being the leader, the international leader of a huge team of astronomers working in a field that didn't even exist when she was taking introductory astronomy only 5 years earlier. Her name's Kelly Hamilton. And, there's just one of the many publications, and she's now a faculty member at Villanova University in Pennsylvania. So what's happening in my field? The opportunities for the young people are just amazing. There are new things we've never seen before for them to work on, even at the PhD level. Another young postdoc at Caltech by the name of Avi Sporer also led a team effort on one of these heartbeat stars, and Caltech's got lots of money, so he got an artist to paint us a couple of heartbeat stars there passing close to each other. We have 180 of these, and these are the light curves. This is time, how bright they are, and they have different kinds of blips depending on the orientation of the stars and how they get stretched. You'll notice that there's some colored curves in there. The data are black, and the colored curves are fitted to the data. Well, the theory for that we found in a paper published by a then young postdoc named Pavan Kumar back in the 1990s. Pavan thought, what would happen if stars did that? And he calculated it, but nobody could test it. These little blips are so tiny you can't see it from ground-based data. And so for 25 years, nobody knew if Pavan's work was worth anything whatsoever. And then we found these heartbeat stars, and you can look. Those colored curves, we didn't force those. There are no free parameters. They fit the data. And so we sent him an email. He works in Texas now in a completely different field. And we sent him an email saying, you know that work you did 25 years ago? You were right. And he was suitably pleased, as you might imagine. There's a diagram I hope you know. Periodic table. When we look at stars, stars are mostly made of hydrogen. Cecilia Payne showed us that. Helium, you know that helium was discovered in the sun, not on the Earth. That's why it's called helium. It's named after Helios, the word for the sun in Greek, by the founder of the journal Nature. And when he discovered the spectrum of helium in the sun, he named it after the sun. So there are the two lightest gases. There you can see nitrogen, oxygen, carbon, the common things. When we look at the spectrum of a star, we see hydrogen. And we typically see these elements in here: chromium, manganese, iron, cobalt. But I'd like you to look farther down here at the lanthanides. The stars I discovered when I was working here in South Africa, and I found their very exotic and interesting pulsations, strong magnetic fields. When we look at their spectrum, you can see the hydrogen, it's there, but that's not what gets your attention. What gets your attention and what stands out is lanthanum, cerium, praseodymium, neodymium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Those are old friends of mine now, probably not yours. In those stars, there's 1 million times more of those rare earth elements than in the sun. What's happening? That's really strange. The stars have got intensely strong magnetic fields, 1,000 times stronger than in the sun, 50,000 times stronger in some cases. We don't know why the magnetic fields are there. We don't have a good theory for that we're sure of, but the magnetic fields stabilize the star, and the light pushes elements from below. The light's coming from below, and it pushes the rare earth elements to float high in the atmosphere until they're cirrus clouds floating in the high atmosphere of the stars. Cirrus clouds not made out of water vapor, made out of rare earths. And they all sit at different levels, and we can study these stars in 3 dimensions. So they're a unique laboratory outside the sun for looking at stars in 3 dimensions.
But how do you know the rare earth is there? How do you detect that?
Oh, the question is, how did we detect the rare earths? Each element has its own spectral signature because of its energy levels. And so in the spectrum, there will be gaps in the light where it's blocked by the electrons moving at different energy levels, and every single element has its own fingerprint. And when you learn the spectroscopy, you eventually recognize the fingerprint of all the different elements. You not only can tell what's there, you can tell how much is there, what the pressure is, the temperature, the gravity, the speed the gases are moving. You can do amazing things with spectroscopy, but you need to learn to read the fingerprints. Sandy?
Have you come across any that indicate elements that have not been identified on Earth?
All right, the question was, have I found anything that show elements not identified on the Earth? We're not seeing transuranics because things heavier than uranium. They've got very short lifetimes. There are 2 elements that are not here on the Earth, unless we make them in the laboratory, and they are technetium here and promethium here. And you might have noticed, some of you, when I started naming all these elements, I skipped promethium. They have no stable isotopes. Some of my colleagues have claimed to have seen promethium and technetium in these stars, and it's not held up. If it held up, then it would be important because it would mean nuclear reactions are going on in their atmospheres. Let me continue the lecture, and we'll come back to questions at the end. I'm not going to finish with loads of time today, so we'll come back to your questions. Now, on one of these stars, we published something just a couple of years ago where we claimed to have found the roundest object in the universe. Using my field, astroseismology, and the vibrations, we showed that the equator of this star was 3 kilometers bigger than the polar axis. Only 3. That's out of 1.2 million. And so we published this saying it's the roundest object in the universe, and it hit 500 newspapers around the world. It was a cute statement. Here's our artist's impression for our press release. Well, let me take you back in time. When I was an undergraduate in San Diego in the 1960s, I bought a book which was 40 years old called The Internal Constitution of the Stars, written by this famous astronomer, Sir Arthur Stanley Eddington. We met him in his suggestion that the hydrogen fusion powers the stars. We met him in his disgrace in his behavior to Chandrasekhar. This book was fundamental to my education. I still have it on my desk. And Eddington starts the book with these words. He says, "At first sight, it would seem the deep interior of the sun and stars is less accessible to scientific investigation than any other region of the universe. Our telescopes may probe farther and farther into space, but how can we ever obtain certain knowledge of that which is hidden behind substantial barriers? What appliance can pierce through the outer layers of a star and test the conditions within?" Eddington's question was as follows. You look at the sun's entirely made of gas. It's like a fog. How far can you see into the fog? In the sun's case, we can see about 300 kilometers into the gas. We can't see any further. It's foggy. It's another 700,000 kilometers to the center. How do you see the inside of the star? The light can't get out from the inside. Eddington had a good answer to that. That's what his book was about. We can calculate the inside of the star. We understand the physics of gas, we understand gravity, we understand the laws of motion. We can calculate what a star has to be like inside. But on the very same first page of this book, Eddington warns that in science, anytime theory becomes divorced from observation and you can't test your theory, you always go wrong. We never know of a case where we got it right without testing it. What Eddington didn't see coming was that 40 years after he wrote this book, just when I was an undergraduate, we would begin to get a glimmer of what to do, and over my working career, we have polished that. It's called astroseismology. You're listening to the sound of a pulsating red giant. Stars have sounds in them, real sounds, and we can use those to look inside. 2010, the first textbook was written in this field, very first one. I'm one of the 3 co-authors. And so over my career, I went from just getting the glimmers of a new field growing to writing much of this first textbook. If you read the first chapter, I wrote it, and I can guarantee you the first 6 pages are readable. After that, if you're not mathematically inclined, you might not want to look at the rest of the 866 pages of the book. But you're getting it from me today in this lecture, so you don't need to go to the book. It's expensive anyhow, and it's heavy. There's a northern-centric view of the Orion constellation. For us here, of course, it's flipped the other way up. This is not a photograph of the sky. This is a computer-generated image by my friend and colleague from Hungary, Zoltán Kollát. Zoltán is very good with animations, and he's a theoretical astronomer working on the pulsating stars from the theoretical end. And what he did is he took data from a mission that orbited the Earth and measured the distances to the stars. You remember the first distance was measured by Thomas Henderson here in the Cape. We now can measure distances to stars to incredibly high precision, right out to the center of the galaxy with the new Gaia mission. Zoltán programmed the computer to have not just the brightnesses of the stars in this picture, but their distances. I want you to notice we're now going to take a trip to the belt of Orion, thanks to the computer, at 200 million times the speed of light. Please forget Star Trek. Please forget Star Wars, where they hit warp 10 and the stars whiz by. No way. The stars are so far away that even at 200 million times the speed of light, they're not going to go whizzing by. Notice that most of the dots you see in this picture are little tiny dots. Those are the little red dwarfs. And so let's take a trip to Orion. There's some very strange music playing. That semi-classical composition is by a Hungarian composer named Jenő Koller. Every instrument in the orchestra you're listening to is a star. Those are sounds out of the stars. That's music like you've never heard it before. Now, can I really be telling you the truth about that? Can there be sounds in the stars? You know, as you sit there right now and you look at me and you look at the screen, light's entering your eye, it's being focused on your retina and the energy is being absorbed. It's then turned into an electrochemical signal that passes down your optic nerve to the part of your brain that interprets vision. You've got a movie theater running in your mind. I do too, from our vision. So we humans are incredibly visually oriented as long as we do have sight. We say seeing is believing. I take my dog for a walk and she says, seeing's okay. But you want to know something, smelling is believing to a dog. When I was a student in Texas, I did a lot of caving. It's limestone country. We didn't go caving during the day. Why do that? It's dark in the cave. During the day, we went kayaking, we went swimming, we went rock climbing. And when it got dark, we went into the cave. And as we went into the cave, 10,000 bats are coming out. They don't hit each other. They don't hit you. They get out in the dark and they can catch the tiniest little insects that are their food, but they're not using their eyes for that. They're using their ears. Now, as I talk to you, I'm making your eardrums buzz in and out by producing sound. And the energy is being absorbed by your body, and it's being turned into an electrochemical signal. Same signal that goes down to your optic nerve, this signal now goes to a different part of your brain, and you and I experience sound and vision very differently. You can't get in the mind of another creature. All of you know from the people you live with, you can't get in the mind of another human. But if you could get in the mind of a bat, my guess is the bat's got a movie theater running in its mind. It can see the world. It knows where everything is, but it's using sound. So take home message today, you can see with sound. We know how to do it with our instrumentation. We do it in the hospital. We do an ultrasound scan of a mother-to-be's abdomen. And 10 years ago, if I were giving you a talk like this, I would have shown you a picture of the fetus made from the ultrasound scan, because we're so visual. But nowadays what we do is we use a 3D printer and we print the face of the fetus. That's a treat for any mother-to-be, but think of a mother who is either blind or partially sighted. This is the only way for her to see her baby, is with a three-dimensional model like this. So with the sound, we make a model. And that's what I do with the stars. The sounds let me look into the stars and see them in detail, and then in the computer we make models of the stars. And I can tell you that if I shrank the sun down to the size of this fetus's face, I can see the inside of the sun in more detail than you can see the fetus's face here. So let's just have a reminder what sound is. Sound's a pressure wave. Here in this room with the nitrogen, oxygen, gas that you're breathing, sound travels at 343 meters per second. The molecules in the air are bumping into each other. And when I set up a pressure wave, this is to indicate the air molecules. Here's the pressure wave coming out, pushing your eardrum in and out. When I set up a pressure wave, it travels out at the speed of sound, but the information's actually transmitted by the collision of the particles. They actually have to bump into each other. And if the temperature's higher, the particles move faster, the sound speed's higher. So if you can measure the sound speed, you have a measure of temperature. You can also tell the chemical composition. Here's something you've probably done. Go to a child's party, there's a helium balloon. Untie the helium balloon and take a nice big lung full of helium, and then talk like Donald Duck. Why? Helium's very light. And for helium atoms to carry the same energy as oxygen and nitrogen molecules, the helium atoms have to move much faster to carry the same energy. So the speed of sound in helium is 3 times higher than in air. And that's why you get the squeaky voice. And by the way, this won't hurt you from the helium. It's completely inert. There'll be no chemical reaction. Keep doing it and you'll suffocate. You're not getting oxygen. But the thing to be careful of, if you do that with children, people who make balloons often put a bit of talcum powder in them to make them easier to blow up. And so you are breathing a bit of talcum too, and that's something to be careful about. So you can tell the chemical composition, you can tell the temperature. From that, you can get pressure and density. You can tell wind speed inside the star. You can determine what the inside of the star looks like, the thing Eddington was looking for. But you cannot hear the stars directly. Our human hearing has a range of 30 cycles per second, some people maybe 20, up to 18,000 cycles per second for nobody in this room, but for very young people. We all lose our high frequencies as we get older. In England, a man made a device about 10 years ago called the Mosquito. In England, you know, there are neighborhoods where the kids aren't the best behaved. It happens there too, as well as here. And what happened there is shopkeepers who were having problems with just bad behavior from teenagers put the Mosquito up. And it makes, I've been told, I can't hear it, a horrendous squeal at about 18,000 cycles per second, and the kids can't stand it. The adults can't hear it. They come shopping, doesn't bother them at all, the kids stay away. It's controversial. What happens if you bring your dog? It's going to howl and be in distress. What happens if you bring a baby? The baby's going to be in distress. You probably don't know why. So it is controversial. But we can only hear a narrow range of hearing, so range of frequencies. How can I play for you the sounds of the stars? Well, let's look at this beautiful leaf-nosed bat. All of you who are environmentalists, love animals, will agree with me. That's a beautiful creature. It has the ability to put out a sound, focus it with the reflector on its nose, stop screaming, and wait for the reflection of the sound to come back in order to echolocate. That bat screams so loudly it would do ear damage if it didn't disconnect its ear bones. So it disconnects its ear bones, screams, reconnects, and listens. 60 times per second. Evolution is just phenomenal. We have instrumentation that can record the sound of the bats. This bat mostly echolocates at 50,000 hertz and we can't hear it. That's when a bat flies by and you hear this little kind of tick-tick, you're just hearing the low frequency end of a very loud squawk that's beyond our range of hearing. But with instrumentation, we can record the sound. Now, sound for us, in physics, sound has got frequency, it has amplitude, how loud it is, and it has phase. Those very same things in music are pitch, loudness, and the starting time of the note. Same in music as in physics, just different terms. And so we record the sound of the bat, and we just do a key change. All the key changes in music is you keep all the frequency relationships the same, you just divide in the frequencies or multiply and start on a different frequency. But you keep the ratios all the same. Sorry, my bat didn't scream at you. I want to make him scream. Let's see if I can get him to do it. They're actually much louder than that. They almost certainly would be extinct if we could hear them. We don't share the environment with things we don't like. I don't approve of that. That's just a statement of fact. So fortunately, we can't hear them. Now, is that what bats really sound like if you could hear them? And I think sort of. So if you can imagine, all right, that's kind of what a bat would sound like if I had high frequency hearing, there you go. The stars have very low frequencies, and here's a good example of a low frequency animal. That's a warning call of a blue whale. The loudest sounds that they put out are 186 decibels at a distance of 1 meter from the whale. 120 decibels will do ear damage to you and me. 180 decibels is 1 million times louder. If you're in the water in the front of a blue whale, within a few meters, when it lets out its loudest sound, there's enough energy in that sound to kill you from the concussion. What it means is that even though we hunted them almost to extinction, a blue whale in the Arctic and a blue whale in the Antarctic can still talk to each other across the entire planet. That sound is mostly too low for us to hear, but again, we've recorded it with sonar and then done a frequency change, a key change, boosted it into the audible. And so if you can imagine, that's what the whales would sound like if you could hear them. In the same sense, kind of that's what stars would sound like if you could hear them when I boost those sounds into the audible. I have to tell you that I don't do science by listening to the sounds from the stars. I record the sounds, I'll tell you how in a moment, but with mathematics, And with my models in the computer, I work on them directly with the data. We don't do turning it into sounds for fun for you and me. It's not the direct way to do the science, except in the case of Wanda Diaz Merced, who's an astronomer at SAO who's totally blind. She did her PhD in Puerto Rico, and she has begun sonifying the changes in stars so that blind people can sit and listen to that and actually do science by detecting things in the sounds. And she's only just beginning to develop that field. She's a very interesting person, and summer school really should get her up here to do a talk sometime. She's done TED Talks, and she's talked internationally. She's right here in Cape Town. I need to talk to you about oscillations. And so to start with, one-dimensional oscillations. Maybe you did this on strings in school, in science lab. Otherwise, if you play violin, cello, guitar, some stringed instrument, any of you, this is your stringed instrument. There's your violin. It's fixed at both ends. The string goes up and down in what we call the fundamental mode, and here it is moving up and down. And that gives the string its basic pitch. But if there's a node, that's with an N, a point in the middle that's not moving, and the violinist can create that by just touching the string, then one end of the string goes down while the other end goes up, and you get a frequency twice as high. You're up 1 octave. Touch the string a third of the way along, and you get an oscillation like this with 3 times the fundamental frequency. And so in a typical musical instrument, you have frequency ratios 2 to 1, 3 to 2, 4 to 3. These are the things that we call octaves, fourths and fifths in music. They make harmony in Western music. They're low integer ratios. That sounds nice to our ears. At least we've trained ourselves to like it. So this is oscillations in 1 dimension. We're headed to 3 dimensions for the stars. We have modes, individual ways of oscillating, and there are nodes, points that don't move. On the left here is a plot of the pressure wave coming out to your ear, pushing your ear in and out. So this is pressure, this is time, and your ear gets pushed in and out like this if you have a very simple sound. On the right is a diagram that I love. This is a place that I lived much of my life. It's a plot that plots how loud the sound is versus its frequency. And in this case, we have just 1 frequency with 1 loudness. And scientifically, we call that a sine wave. To listen to it, it's boring. It's an electronic whistle. We don't like that very much. What do we do with musical instruments? We decide not just the fundamental, but the first, second, third, fourth, fifth overtones. And as we do that, it changes the shape of the wave and the way it pushes your eardrum in and out. Now, I'd like you to imagine for the moment that instead of me talking to you here, Barry Smith's up here, and he's going to conduct a small concert. Or I don't now know who the conductor of the orchestra here is in Cape Town. What's the name of the orchestra conductor here? Okay. You go down to the city hall, and you're listening to a classical concert. Right here, now. Eyes are closed. First violinist gets up, she walks over to the piano, and she plinks middle A, 440 hertz. And the whole orchestra starts tuning up to it. Everybody's playing the same note. They're all in tune. Same frequency, 440 hertz. But with your eyes closed, you can hear the violin. You can hear the French horn. You can hear the trumpet. You can hear the bassoon. You can hear the oboe. You can hear the flute. How do you tell all those instruments apart if they're all playing the same note? The timbre of a musical instrument depends on the excitation of these higher overtones. And the same's true inside of a star. We'll come back to that. Let's go on in the musical instrument field. In the orchestra, we've got drums. So here are drum heads. And over here, we have the fundamental radial mode. The drum's 2-dimensional. It's circularly symmetric. And if you hit the drum right in the middle, it'll also blade up and down like that. Drums don't like to do that. I was a drummer at school, and if you hit a drum right in the middle, it goes thump and it stops. That's not where we play the drum. We play much closer to the rim to get sound out of timpani or other drums. In the radial modes, you can have a node, but it's a circle rather than a point, and the drum does this. You can have 2 nodes, which are circles, and the drum does that. But being 2-dimensional, you can also have a line across the drum to produce a non-radial mode, and the drum does this. There's the quadruple mode in the middle. And you can even mix the non-radial modes with the radial modes, and the drum head goes all over the place. Drums don't make nice musical tones usually. And the reason is that the frequency ratios you get are something like 147 to 83 and 414 to 197. not 2 to 1, 3 to 2, 4 to 3. So drums go boom, cymbals go crash. And mostly stars, if you listen to them, are very dissonant, mostly. You can pick some good ones if you want to make music for fun. The violin itself is designed to have nodes to produce the beautiful sound of the instrument. This is done as an art form rather than by physics. These are violin front face and back plates that are suspended by very thin wires, and then sounds make them resonate, and there's carbon dust sitting on the surface, and the carbon dust settles into the nodes of the various overtones of the violin plates, and that's the way you get a beautiful sound out of a violin. By trial and error and by art up till now, we're beginning to reproduce it physically, but nobody yet has produced a computer violin that's got the beautiful sound of the best instruments. So going to 3 dimensions, here are the stars. Stars oscillate like this in the radial mode. They swell and they contract, they get hotter and cooler. The inside of the star is a node, it's like a point on a string. The surface is an antinode. And so a star is very much like a wind instrument or a woodwind or an organ pipe. The nodes inside the star are concentric shells. But the star can oscillate in non-radial modes, like this one, the dipole. There's one mode that goes up and down in space, and then there's another one rotating this way and another one rotating the opposite way. Boy, I'm going to put that to use in just a moment. And just one more set of examples. These are the quadruple modes that have 2 nodes. One stretches the star like this. This really happens. Stars do this. The tesseract mode has 1 line of latitude's a node and 1 line of longitude. And the sectoral modes, it's all lines of longitude. There's another set over here going the other direction. We've now got a way to look at the rotation of a star inside, and I'll show you the remarkable result of that. This is a supercomputer movie made of an oscillating star, a pulsating red giant with sounds in it. It took 2 weeks on one of the biggest computers in the world to generate this movie, and the physicists only put in the physics of convection, of hot rising columns of gas and cool falling columns of gas. But in stars like the sun and this red giant, that's what starts the star to wobbling. So they didn't put anything in to say to the star wobble, they just put in convection, and they got the wobble. If you could get up close to the star and speed it up, the colors indicate temperature. It would do something like this. So is this what I do as an astroseismologist? I get out under the stars with a big ear and I listen to them? No. Sound can't travel in a vacuum. No sounds get out of the stars. How do I hear the stars? Well, I've put my phone away. Yes. Let's pretend this is my phone. You've all kept yours put away, thank you. And I take out my phone and I call my wife, who's off in some other building, and I say, "Hello, wife," and she says hello back to me. And out of my phone comes her voice. Am I hearing my wife? No. She spoke into her phone. With electronics, we have recorded frequency, amplitude, and phase across all the frequencies she speaks with, and we've turned it into a microwave, which is long wavelength light. And we sent the microwave up to a mast and then down to my phone. We've picked up the light, long wavelength light, and deciphered it. It's got the information, run a speaker, and reproduced the voice to very high fidelity. I'm watching the stars vibrate, and their light comes to me, and the light's carrying the information about the sounds. And so the Kepler mission's watching the brightness of stars, and it's that brightness that we're using to determine what the sounds are in the stars. Now, I want to do a little history with you. These are data that I took in Sutherland 40 years ago. I'd have to get close to that. Where this is time and days. It's a half a day because the night's only half a day long, even in winter. This is how bright the stars are, and each of these little light curves of the star varying in brightness is 1 night of observation. There's 1, 2, 3 nights, and then I come back the next month and get 1, 2, 3 more nights. And I come back the next month and the weather's a bit better and I get 1, 2, 3, 4, 5 nights. And that bar right there is about 2% in brightness. This is a major effort for an entire observing season to observe one star when it's clear, when it's dark, and when I've got the telescope. Kepler comes along. We met it yesterday, and there's one star from Kepler. It's all squashed. This is 4 years, 1,470 days. This is brightness in parts per thousand, and each of those points is precise to a part per million. And there just are almost no gaps. Here's just 7 days to blow it up. Every single variation you see in there is real. The errors are way smaller than the data points, and I've got 200,000 stars. And so the discoveries just come pouring out. One of the important kinds of variable stars is called a Cepheid Variable. This is another animation from Zoltán Kollát. There's his name right there. In Hungarian, he would be Kollát Zoltán. They put their surname first. And what Zoltán did was he created a little horn, a musical instrument, in the computer, and then made a graphic of the shape of that horn. But he gave it the frequency response of a pulsating star called a Cepheid variable that gets bigger and smaller. And then he programmed his instrument to play a Bach prelude. And so here is Bach. As you've never heard him before, the instrument playing Bach is a pulsating Cepheid variable. Most of the stars are very dissonant. He's picked one that doesn't sound too bad. Why are these important? Because 110 years ago, a little bit more, Henrietta Leavitt, working at Harvard College Observatory, discovered what's called the Period-Luminosity Relationship for Cepheids. The longer the period for the pulsating star, the brighter it is. That is fundamental to our understanding of the universe. This is Henrietta, which is a young astronomer. She did not live long. She died at the age of 53, but here she is in her prime doing her work at Harvard College. And she says it's worthy of notice the brighter variables have the longer periods. Here's a plot from her discovery paper showing how bright the stars are and how long they take to pulsate. 1 day, 10 days, 100 days. There are two kinds. Here's a more modern plot showing the same thing. It's easy to measure how long it takes the star to vary. These stars vary so much you can watch them with your eye do it. You just measure it takes 10 days to get brighter and dimmer, and once this is calibrated, you come along, you know how bright the star really is. If you know how bright it really is, how faint it appears tells you how far away it is. Because as stars get farther and farther away, they get fainter. This is the method we get distances outside of our galaxy, the main method. This is the method by which we determine the expansion rate of the universe. We tell you how long ago the Big Bang started, what's going to happen in the future. These stars are fundamental for this. This was put to use just 10 years later by Edwin Hubble, whose name you'll know from the telescope named after him. He took Henrietta Leavitt's period-luminosity relationship and was looking at the spiral nebulae. At that time, these little spiral nebulae we were picking up with telescopes, some astronomers thought they were galaxies like the Milky Way, far away. Other astronomers thought they were gas clouds inside of the entire universe, which was only the Milky Way. And in 1923, this picture right here, Hubble took a picture of the Andromeda Galaxy. Now, this is a ground-based picture nowadays. Amateurs can take far better pictures than Hubble could 100 years ago. This is state-of-the-art with the biggest telescope in the world, and this can be done by any amateur with a small telescope now. And up here, he put VAR exclamation point between those two lines. He's found a Cepheid, 6th of October, 1923. And the next morning in the news, humans' view of the entire universe expanded dramatically. He had shown that the Andromeda Galaxy was another galaxy like the Milky Way. He thought it was 1 million light years away. It's actually 2. There was a calibration error that was fixed 25 years later. And we still use these stars to determine the distances to galaxies, measure the expansion rate of the universe. So let me show you how astroseismology works, and then we'll answer some other questions too. Here's the main physics diagram in the lecture. This is supposed to be a cross-section of a star. There's the center of the star. This is its surface, and it has sound waves bouncing around inside. Some sound waves go from the surface right down to the middle and come out again. Those are the radial modes, like the Cepheids. Some have got nodes on the surface, so they're being stretched, and those waves aren't pointed towards the center. The star's much hotter deeper down, so the sound moves faster and it's refracted back and bounces around inside the star. This wave to quite a deep depth, this one much more shallowly. In the sun, we can see 2 million different oscillations in sound waves, and that lets us determine the sound speed from the surface of the sun to the core to a precision of better than 3 0.3% throughout the entire sun. So when I tell you the center of the sun has a temperature of 15.4 million degrees, when I tell you that the center of the sun, purely made of gas, mostly hydrogen, is 8 times denser than that gold wedding ring I'm wearing there, that's not calculated. That's not out of Eddington's book, How to Calculate a Star. That's not guessed. We can see it. We can see it in the sounds, because the sounds that go to the center come out. And if the density and temperature were different, the frequencies on the surface would be different. We can see right into the heart of the sun where the nuclear reactions are happening. Now, haven't you been sitting there thinking, well, why do the stars have sounds in them? You've been repeating that in your mind the whole lecture? Where do these sounds come from? You have. You know, the Earth's got sounds in it, sometimes. Let's look and see where the Earth gets sounds. The Earth gets sounds from earthquakes. And here's a graphic by a Japanese geologist from 2011. I've jumped forward to the end of February. Here are the main islands of Japan. Honshu, the main island. Tokyo's here. Hokkaido in the north. Kyushu and Shikoku off here to the west. Each little circle represents an earthquake of magnitude 4.5 or larger. And by the end of February, there have been 838 already in Japan. And we're just going to watch what happens over the next couple of days. I hope you find that scary. I certainly did. That's what my office looked like 3 hours later when I could get back into it. I work in Japan every year. I had been at the epicenter just a few days earlier skiing in the Japan Alps, was back in Tokyo, 10 stories up, and the whole building was shaking and waving. We tried to keep an international meeting together for another 12 days. I stayed on in spite of Fukushima. We didn't succeed in keeping the meeting going, but the whole Earth kept shaking. And I have to tell you, as scientists, we did something you might not approve of. I can remember sitting around in the pub at a 5-star hotel in a national park where we were trying to hold this meeting, but had only a couple dozen people there. And we had some major earthquakes while we're sitting in the evening. And we looked at each other and we said, you know, we're really sorry, we're sad that 20,000 people have just died. But this is really interesting. For us as scientists, leaving aside the terrible human calamity that it was, to be part of the Earth oscillating like that was exciting. That set up sound waves that reverberated through the Earth for a month. And the geoseismologists come along and tell you that the inner half of the Earth's made of iron. The outer part of that's molten, the inner part's solid. How do they tell that? From the sound waves that penetrate into the Earth. How do I do that for a star? A star has no solid surface. There's the sun as you know it. I took that picture off the north coast of Norway in the middle of summer a few years ago. It was midnight. And when we got back to Tromsø, I have a Norwegian astronomer friend, Jan Erik Solheim, and I was talking to him about the midnight sun. And he told me that he had a woman visitor from California, Los Angeles, a couple of years before that. And you must all know that Californians are all very strange people. Being a native, I can say that. And she said to Jan Erik, you know, when I get home, I'm suing my travel agent. She said, I came to see the midnight sun, and all I got to see was the regular old sun. We have no idea what she thought was going to be up at midnight, some different sun. But I have to tell you, the regular old sun is not so regular. I want to show you a spectacular movie taken from the Solar Dynamics Observatory. This movie's sped up by 360 times. This is a telescope orbiting the sun, and it caught a flare on the limb of the sun right here. This is a magnetic field reaching out into the corona and cooling the gas, and the cool gas, 50,000 degrees, is falling back onto the surface. The computers put in the Earth to scale. And if you, for the moment, can tear your eyes away from the terrible beauty of this falling gas, look at the rest of the surface of the sun. It's seething. Hot columns of rising gas are coming up. Cool columns are falling. Magnetic fields are snapping. Flares are going off. Materials being shot across the surface. The sun is an incredibly noisy place, way beyond any thunderstorm you can imagine. And all that sound sets the whole star to vibrating in these musical notes that we can then use to study the inside of the star. Let me show you some of the things we found for the sun. This graphic from my colleague Sylvain Korzenik at Harvard shows the inside of the sun. This is the sun's rotation axis. This is its equator. That's the center, and this is the surface. We've known for centuries that the equator of the sun goes around once in 26 days. Here's the color plot down here. And the poles take 35 days.